Uh, Hello everyone. Today we have the pleasure to listen to Colin Hill from Columbia University. Colin did his PhD at Princeton, and then he was a postdoc at Columbia, and then a postdoc. Then afterwards, he was a postdoc at IS and Princeton again, and now he's a faculty, joint faculty between CCA and Columbia. And he'll be telling us about his new research, I guess, from the CA using the CMB and early detecting new physics using CMB and some other things like this. So,
We'll see how much.
all right. Yeah. Okay. Take it away.
Okay. All right. Thanks, Alex. I guess any interest in saving my voice? So
Yeah.
I'll take this off.
I think you have to keep that on.
Yeah,
Should I keep it on?
Yeah, that's
All
the
right.
policy, yeah.
Can you hear me if I have it
not
on?
very well,
Okay.
but that's the rule.
Okay. All right. Well, I don't want to violate the rules.
If you want us to get you a lighter one, we might have a lighter thing.
I should be okay. I'll take some drinks of water if I need to.
Sorry about that.
Okay. Can people on Zoom also hear successfully? I don't know where the microphone is, but.
The microphone. Sorry.
Yes, we can hear you.
All right, awesome. Okay, so thanks a lot for having me. So I'm going to talk about searching for new physics in the Universal Site CMB using the latest data from the Atacama Cosmology Telescope ACT. So I'm going to talk about a few different papers going back to some work from last year with this cast of characters, and then the newest paper. I guess the bottom of my slides are slightly cut off, but that's okay. The newest paper is with the ACT team. It came out a few weeks ago. Okay, so this isn't, I'm not going to spend a lot of time kind of reviewing the situation with H0, but that is kind of the underlying motivation for looking at the types of new physics that I'm going to be focusing on. My personal view on the observational situations that remains unclear. I'm sure everyone's familiar with this, this problem, but the basic issue is that indirect inferences of H0, assuming the MCDM model from CMB data and other cosmological data sets, tend to give somewhat lower values than what we get with direct measurements at late times in the low redshift universe. For example, using the distance ladder calibrated with Cepheid variables. But I do think that there are individual measurements at late times that are certainly consistent with the indirect inferences. So my personal view is that the observational situation remains unclear. But nevertheless, I think the situation has motivated us to think about types of new physics that we wouldn't otherwise have thought about in cosmology. Certainly for me, that's the case. And now this boils down to the question of how can we change the cosmological model in such a way that we infer a higher value of H0 from CMB large scale structure data. And this turns out to be a much more difficult problem than you might have initially thought. So first of all, late time theoretical modifications are highly constrained by the relative expansion history data that we have in the redshifts. For example, from PAO distances and type 1a supernova distances. And this, by relative, I mean here without referring to an absolute distance scale as calibrated from H0 measurements. So I agree with this statement from Lloyd Knox and Mario Smoleta's Hubble Hunters guide, where they write that we single out the set of solutions that increase the expansion rate in the decade of scale factor expansion just prior to recombination as the least unlikely solutions to be successful. So maybe not most likely, but at least the least unlikely. So that's what we're going to focus on. So the generic consequence of such modifications is that there are new signals and they cause a microwave background. So we can look for them using our mascot down here.
There's a way to hide that, but we need to know who's the host.
He's sharing the screen, so should
I mean,
go
it's
about
not-
the microphone,
It's not a crisis. Oh, there we go.
Yeah.
Great.
No, that's fine.
Awesome.
You can just you don't have to check.
All right, so now you can see our mascot like it's 30 seconds. All right, so that's the setup. So I'm going to first introduce you to our latest data from ACT and consequences for H0. There'll be a brief technical aside here about the accuracy of Einstein-Boltzmann codes, and then I'll focus on the early dark energy model, both the pre-ACT DR4 constraints from last year, and then the latest results from ACT DR4. Time permitting, I'll say some words about small-scale baryon-clumping models, and then I'll conclude with a look to the near future. Okay, so let's start out with inferences of H naught from ACT. First in lambda CDF. So in case you're not familiar with our experiment, it's located on Saratoga in the Atacama Desert, which you can see is a great place to do CMB work. This is actually the ground screen around the telescope. The telescope is inside of there. There's a picture of the telescope itself. We've surveyed about half the sky over the last few years. ACT has actually been observing since 2008, but we started doing these wide scans in 2016. So we've covered about 20,000 square degrees, and we have, at this point, 5 frequency channels, although the data that I'll show here is based on observations at 2 frequencies. And we're a team of about 80 or 100 people now. This is our last in-person gathering back in March of 2019. Okay, so our big data release 4 came out last year. The 2 key papers for cosmology were Iola et al. And Choi et al., which I highlight up here, and I'll focus on those papers in this talk as well as more recent follow-up work. But there's all sorts of other science that we can do with this data, of course. So I just want to advertise a few of the other papers here. For example, I worked heavily on building component-separated maps of the CMB and the thermal Lovich effect. You can also find lensing maps. We have a catalog of over 4,000 entity clusters and all kinds of other great stuff. And all this data is public, and you can find it on the Lambda server. Okay, so this data release 4 includes data that was collected between 2013 and 2016. It covered about 17,000 square degrees in total, but the survey varies widely in depth. So the deepest regions are these ones labeled Deep 5-6 and Boss North. And those total, well, those 2 regions total something like 2,500 square degrees, but the cosmological analysis that I'll show uses data that spans about 5,400 square degrees. So in 2016, we went wide. So we covered this whole blue region that you see, but the data was shallow enough that most of it wasn't used for cosmology. But we've been surveying that same region in the past few years to much greater depth, and our next data release will include data that covers that entire region. Okay, so you might ask, why are we still measuring CMB after all the progress that's been made in the past 20 or 30 years? So I just want to show you a couple of pictures to highlight that we're actually still improving things dramatically. So this is a patch of sky covering about 600 square degrees from Planck at 143 gigahertz. Now let's combine Planck and ACT. If I flip back and forth between these 2 pictures, hopefully you can see how the small scales in this picture just snap into focus. So that's coming from the fact that ACT has both significantly higher angular resolution than Planck, as well as significantly lower noise, higher sensitivity than Planck. So this is a combination of the 2 at the map level, but for what I'll discuss for analyzing things separately, power spectrum.
The little black dots, SC. Oh,
yeah, so the blue spots that you see on small scales are shadows, CASAs, CMB, SC clusters, and then the positive red spots are radio and infrared point sources. So with the great angular resolution we have, we can pick out all these small scale features in the microwave sky. All right, so now I'm fast forwarding through probably a half decade of really hard work by dozens and dozens of people to get all the way to our main cosmological data product of interest in this talk. So these are our foreground marginalized CMB power spectra, the TT power spectrum up at the top, EE, E-mode polarization, the TE cross correlation down here, and then we have a moderate measurement of the lensing B modes around L1000. So one thing I do want to highlight initially is that we don't measure the largest angular scale modes in the sky, in particular in temperature. And the reason for that is just that atmospheric noise from the ground makes those modes highly contaminated and difficult to measure. So we cut our TT power spectrum at L600. And so it's important for us to combine with ancillary data sets, for example, from WMAP or from Planck that covers the lowest multipoles of temperature. We can do a bit better in EE because the atmosphere is unpolarized to lowest order. Okay, we're not the only game in town, of course. So this is the compendium of CMB measurements as of last summer. So the SPT3G and the very latest BICEP tech results not on here, but everything else pretty much is. And you can see that we have this nice consistent picture that spans orders of magnitude in angular scale, which is quite well fit by the lambda CDM model. which is the theory curves that's shown here. But as we'll discuss in this talk, maybe we're seeing hints for some deviations. Okay, so first I'm going to walk you through the lambda CDM analysis, and then we'll talk about extended models. So the first thing that's of interest for ACT DR4 is that it's a completely independent check of the cosmological results from WMAP and Planck from a very different instrument with completely separate systematics. So the key parameters to keep in mind I've listed here. I'm guessing almost everyone in the room is already familiar with the 6 parameters of lambda CDM, but I've listed them there for completeness. And then the two interesting, there's several interesting derived parameters, but the two that we'll focus on here are the Hubble constant and then the redshift zero fluctuation amplitude, sigma 8. So here's a triangle plot with the constraints from WMAP in yellow, Planck in purple, and ACT in blue. And for the purpose of this plot, you don't need to study every panel carefully, but mostly you just want to sort of do a magic eye thing and notice that everything overlaps pretty nicely. So we have good consistency between the lambda CDM parameters inferred from these 3 data sets. More quantitatively, ACT is consistent with WMAP at about 2.4 sigma, and with Planck at about 2.5 sigma within the global lambda CDM parameter space. And the only reason that those are not even more consistent is one panel here, omega baryon H squared in NS, which fluctuates a bit strangely, and that's driven mostly by the first peak in TT, which we can talk about if people are interested. But the basic picture is lambda CDM fits the ACT data well, and given this consistency, we can combine ACT with WMAP, which are very complementary in terms of the range of angular scales that they cover, to form a data set with statistical power that approaches Planck. So that's what we did. So this is a plot that shows the joint constraints from ACT and WMAP in purple, Planck in light blue, and then ACT plus Planck in dark blue. And again, if you just sort of let your eye relax and look to see if things are consistent, you can easily see in this case that ACT plus WMAP is in great agreement with Planck. So zooming in on the H0 posterior, which is of interest to us today, you can see that everything's perfectly consistent, and we get H0 values around 67.5 to 68, where the error bar from ACT plus WMAP is within spitting distance of Planck, although Planck is still low. Okay, so we obviously tested these results against a huge range of variations in the analysis. So varying the L range that's used, looking at TT or TE or E only, looking at our 2 frequency channels separately, and then also analyzing different patches of sky. And focusing just on H0 here, the results are stable to all these variations. However, there was one thing that I noticed that after the DR4 results came out. This I think came up last winter while I was working on the Kennedy analysis, which turned out to be something that had been missed and has a small impact on our cosmology. And that's related to theoretical considerations of the Einstein-Boltzmann codes that we use to calculate linear theory observables in cosmology. So the 2 famous codes that are used these days are CAM and CLASS. And these come with some default numerical accuracy settings. We're solving a couple of different equations, and there's always some tolerances in your code for the numerical accuracy. And if you run these out of the box with the default settings, it turns out that it's not quite accurate enough for the analysis of the ACT data. So in particular, the lensing calculation needs to be done at higher accuracy. So this is just illustrating what happens. This is a subtle effect, but it turns out that it's just barely noticeable for ACT DR4. So this is the lensing potential power spectrum on the left, with the default accuracy calculation from CAM shown in orange, and then higher numerical accuracy calculations shown in light blue and in dashed purple from CAM and CLASS. And you can see that the 2 codes agree very, very closely after you crank up the accuracy settings. And this then impacts the primary CMB through the effect of gravitational lensing on the primary CMB power spectrum. So the plots on the right show the fractional change in TT, TE, and ED. And you can see that it's on the order of a few percent, ranging up to 10% as you get into the damping hill. And it turns out that with ACT, this actually has a small but noticeable impact on our cosmological parameter inference. So we reran the lambda CDM parameters. This appeared in the paper that just came out a few weeks ago in an appendix. So this is again the triangle plot of the lambda CDM parameters, and it looks remarkably stable, which it is, but it does shift a couple of the parameters by about a third of a sigma. And this is a theoretical accuracy setting issue, so it's not like this is a systematic effect that it's hard to understand. We just have to run things at higher accuracy. So this shifts our H naught up by about a third of a sigma. It goes the quote unquote right direction to help, to help reduce the tension with shoes, but it's a small correction. So our final baseline result from MAC plus study map becomes 67.9 plus or minus 1.1.
Are you sure the problem is fully solved?
Yeah. We tested the settings very thoroughly. In fact, so we then wrote a whole paper. So the order of operations here is funny. So we discovered this issue while doing the ACT analysis, but we then had to redo the whole order of the dark energy fits, which took several months. But in the meantime, I wrote a theory paper with Fiona McCarthy and Matt Montemachero. Fiona has just moved to CCA actually last week, and Matt's at Perimeter Institute. So what we did in this paper was first to look at this numerical accuracy setting question. So this is easy to fix. You just crank up the accuracy parameters in class or CAM. But also, as I mentioned, this comes into the lensing calculation. And it turns out that baryonic feedback corrections that see in the power spectrum also have an impact in this context. So your inference of parameters from the primary CMB is affected by things like AGN feedback, amplitude shifts, which I think is kind of amazing. But I'm not going to talk about that in any more detail here. I'm just going to focus on the numerical accuracy setting question. So this is a plot that shows the fractional bias in units of sigmas that you get as a function of the sensitivity of your experiment. So higher L max means you're sensitive to more and more modes in the CMB. And wherever these curves for different parameters cross 1 sigma, you're getting a non-negligible bias. So as you can see, as you get to very high sensitivity experiments, you get a multiple sigma bias on things like H naught or omega CH squared. So this turns out to matter, but it's easy to fix. You just have to run your Boltzmann codes with higher accuracy. So for CMBS4, this would have been a catastrophic mistake if we hadn't noticed it.
Yeah. What else did the baryonic feedback corrections come in? Or is this is it a similar trend? Or?
Yeah, it looks pretty similar. In that case, instead of these curves going up, they tend to go down because baryonic feedback smooths out the matter distribution on small scales.
Relative to these.
That's right. But it looks very similar in terms of the range of angular scales that's affected. It's less dramatic than these biases. Instead of getting a 6 sigma bias, you get a 2 sigma bias, but it is still noticeable. In this paper, we present some strategies to mitigate these biases.
But you're not showing us what the baryonic feedback does.
No, this talk wasn't supposed to be about that in detail, but I can tell
Right,
you
but it
afterwards.
sounds catastrophic because it would be very poorly understood, I would think.
Yeah, so we're lucky in the sense that we can parameterize the shape of this impact on the matter power spectrum. And with a simple 2-parameter model, we show that for all the hydrosims we tested, you can marginalize those parameters and basically mitigate the bias at minimal cost to the constraints of cosmological parameters. I can show you the plots up.
Yeah.
Okay, so good. So then this is the updated picture, I'd say, of lambda CDM cosmology from ACT 4. So the ACT results are the ones that are shown in orange, and these small shifts upward are from this higher accuracy correction that I just mentioned. And I have the latest shoes results in purple. There's been a new measurement from Riesel that just came out a few months, 10 months ago, which came down slightly, interestingly. And then the TRGB results from Wendy Friedman's group. So, if you look at the latest results, it's a 3 sigma difference between actual study map and shoes. For Planck, it's more like 3.5 sigma. Whether this is a crisis, I don't know, but still something interesting. And of course, as I mentioned, there are other measurements. In this case, I'm showing TRGB, which are statistically consistent with the early universation. But nevertheless, let's look at some models that could potentially yield higher H naught from the same data. So the bulk of the talk now is going to focus on this early dark energy model. So first, I'll review the construction of the model, talk about some analyses that we did last year, including with Misha, who was here, and then I'll talk about our latest paper with the ACT. Okay, so let me just remind you about how this particular model, and sort of this whole class of models, works to yield a higher value of H naught from the CME. So everything here is really centered around the impact on the sound horizon, which is imprinted in the CMB. So this is the distance that an acoustic wave could propagate in the primordial plasma if it's set off at redshift infinity, time equals 0, until the time of recombination. So it's given by this simple integral to sound speed, Cs dz over h of z. And why do we want to decrease the sound horizon? Well, the thing that we measure in the CMB is the angular size of the sound horizon, which is basically just given by the inverse of the peak spacing in the power spectrum. So that is something that's measured at incredibly high precision. We can't mess around with this. That has to stay fixed. But if we decrease RS star, then in order to hold theta S star fixed, then we also have to decrease the angular diameter distance to recombination. And to do that, we increase H naught, since distance is scale inversely with H naught. So that's how we infer H naught really from CDM measurements. Now, in Memphis CDM, there's only a few parameters that you need in order to calculate the three-dimensional sound horizon. That's the physical densities of the different constituents of the universe. Now, the idea in these modified cosmological models is that we're going to introduce some new constituent with some new free parameters that we can adjust that are going to change RS star. So we're going to change the sound horizon. And in particular, in EDE, we're going to accelerate the background slightly, so increase H of Z just prior to recombination, which is then going to decrease the sound horizon. So that's the basic physics. All right, so how do we actually implement this in a physical setup? So I'm going to focus on models where we introduce some new pseudoscalar field phi, which is going to serve as our source of early dark energy. So this is going to be a very light scalar. So initially the field is going to be frozen on its potential due to Hubble friction. So if you look at the Klein-Gordon equation, the second term here is dominant at early times when H is much, much greater than the mass of the field. So during that epoch, it will act as another contribution to dark energy. Eventually, as H decreases and becomes a quarter of the mass of the field, then it will roll down its potential and eventually oscillate around the minimum. And at that point, the effective equation of state of this new energy source will depend on the shape of the potential. Now, in order to have an impact on the Hubble problem that I just, using the mechanism I just told you about, where we, change the sound horizon, we need this to happen just prior to recombination, which, if you put it in numbers, tells you that the mass of this field needs to be of order 10 to the minus 27 electron volts. So it's an incredibly light scalar, much lighter than anything in the standard model. And so that motivates the consideration of axion-like potentials in which the light mass is protected by a shift symmetry. Good. So I'll show you the shape of the potential in just a minute. But the final consideration, which is important, is that we need this stuff to go away very quickly. So it's going to come in, it's going to briefly accelerate the background, but then we need to get rid of it quickly so that way it doesn't mess up anything else that happens in cosmology at late times. So we want the late time equation of state W to be greater than 0, so that way it redshifts away faster than matter. So that has an impact on the shape of the potential. So the canonical type of potential that's been considered in this context is this axion-like potential with a 1 minus cosine phi, but raised to a power n, where n has to be greater than or equal to 2 in order to satisfy this constraint here. So, near the minimum, you could perform Taylor expansion, and then it's easy to calculate the effective equation of state as a function of this index n, and you can see that if you put in n equals 1, then things aren't going to be great because it's going to act like a source of cold dark matter at late times, which is not good. So this is the basic sort of parameterization. The other thing I'll point out is that for the models of interest here, the axion decay constant f, this potential has to be of order the Planck scale. So from a model building perspective, that's maybe unappealing, but nevertheless, that's how the numbers work out. Okay, so that's the sort of physical parameterization of this model. The parameterization that we're actually used for the data analysis is a little bit different. So the way to look at this is to look at the fractional contribution of this EDE to the total cosmic energy budget as a function of redshift. So for the type of model that can have an impact on the Hubble problem, this is roughly what it has to look like. So we need something like 10-ish% of the total energy density of the universe to be in this form at redshifts around matter radiation equality. And then it has to decay away quite fast. So the parameterization that we'll use is given by this critical redshift ZC, which is where this contribution peaks, and then the amount of the fractional amount of this EDE at that redshift called FDE. And then the final parameter is just the initial displacement of the field on its potential, which we call theta I. And I won't get into this yet.
So what causes the ripples in the decay?
Yeah, so that's just from the oscillations of the field around the minimum of the potential. Yeah. Yeah, so as we'll see later, if the field starts very close to the minimum of the potential, then you can get curves like this where you don't actually even really see the oscillations. We'll come back to that. Good. So I'm not going to talk too much in detail about the last point, but it's worth remembering that there's a very nonlinear relationship between these parameters and the actual parameters in the scalar field potential. All right. So why is this model interesting? I think it can be summed up basically in this slide. So you can compute the CMB TT power spectrum or the polarization power spectrum in this model, and compare it to lambda CDM, and you can find formulations of this EE model where the power spectra are completely indistinguishable, but the value of H naught is significantly higher than it is in lambda CDM. And the plot on the right just shows the fractional difference between these two curves. So you can see it's staying within 1% all the way to 3,500. And this is well understood. It's caused by the decrease in the sound horizon that I just told you about earlier. One comment that I will make is that it's very important to model the perturbations in this EDE field. If you neglect the fact that there are perturbations, you'll get the shape of this power spectrum completely wrong at large scales and you'll get the wrong answer. Okay, so that's the CMB. Last year, we took a closer look at other cosmological statistics that are predicted in this scenario to see if they're also, let's say, stable with respect to the lambda CDM predictions. And it turns out there are differences. So in particular, this is a plot of the matter power spectrum P of K, the linear P of K. Again, with lambda CDM, same models I showed in the previous slide, lambda CDM in black, EE in dash red. And now you can see differences by I, even on this log scale. If you look at a ratio of these curves, you can see that there's differences on the order of 10%, on linear scales. So this tells us that, a combination of large-scale structured data, for example, weak lensing surveys, can have a big impact on the viability of such models. So you might ask, what actually drives these differences? Is it due to EDE-related physics? It turns out the answer is not really. So it's actually driven primarily by shifts in the standard cosmological parameters that are required to preserve the fit in the CMB. Someone could actually read that off from triangle plots, comparing fits to CMB data. This is actually fit to Planck plus shoes, plus a couple of other data sets from Smith et al. Where lambda CDM is in blue, EDE is in red. And the key panels to focus on are first here, the cold dark matter density omega CDM. So you see this big upward shift in omega CDM, and the physics of this is simple. The EDE field is acting to suppress the growth of perturbations slightly at other times. It's contributing an early ISW type of effect due to the acceleration of the background. And to compensate for this, you have to crank up the amount of cold dark matter. The other shift that's noticeable is an increase in scalar spectral index, NS, which is related to exactly the same physics. So the implication for late time parameters is that sigma 8 and omega n will increase, and that leads to an increase in this S8 parameter, which is probed by cleansing measurements. So we looked into this last year in some detail. The first thing that we tried to check is whether one sees evidence for this model just looking at Planck primary CMB data alone. It turned out that nobody had actually done that, or at least hadn't shown it in a paper. So our starting point was to fit the Planck TT, TE, and EE data in this early dark energy model. So what I'm showing here constraints on the three EDE parameters that I mentioned, then H naught and sigma 8. And in the case here where you fit this Planck data alone, there's no preference seen for this model. So if you look at this posterior for the amount of really dark energy, it's a sharply peaked upper limit at 0, with a 2 sigma upper limit of about 9%. Okay, so then we looked at a whole bunch of different combinations of data sets. So in this particular paper, which came out in March 2020, we looked at Planck plus things like DES, HSC, and KIDS. And the basic upshot was that the combination of any of these data sets on their own without shoes always just leads to a peak at 0 for this FDE parameter, which gets tighter and tighter. And the tightest constraint that we derived was in this paper with Misha Ivanov last year, when he's, I believe, still here. And the likelihoods that we used in this analysis were Planck, CMB again, S8 constraints from DES, HSC, and KIDS, and then this effective field theory of large-scale structure likelihood, which Misha, Matthias, Marco, and others have constructed for the BOSS data. And this is the tightest upper bound that we obtained on this model prior to the recent work with ACT. So in this case, again, we just see an upper limit on FDE, which is now this panel here, where the blue curve is the one with all the data sets thrown in, and the upper limit is FDE less than 5% or 5% confidence, which is well below the amount that's needed to resolve the Hubble dimension, which is of order 10%. And again, H naught does not really shift. The H naught is up here. You can see that it's quite stable, and there's still a 3.5 sigma attention with this. So
sorry, I just want to make sure I understand. What you've added is you have S8 in there, and so that limits what you can do with the Omega matter.
Yeah.
And so
exactly.
So you can't fix the problem.
Those two things go in opposite directions. Yeah.
Question, for what end you had a potential?
Yeah, thank you. Yeah, so for all these analyses, we held n fixed to 3. And the reason for this is that n has to be greater than or equal to 2. You could choose 2. We've experimented with using 2. You get very similar constraints qualitatively. The computations are a little bit easier to run with n equals 3, so we use n equals 3. From a theoretical perspective, I think both of these involve some fine tuning, because you're basically tuning the first set of terms in a Taylor expansion to 0 without any symmetry that dictates that. But yeah, we use n equals 3 for all the analyses here.
Instead of taking some fixed and suppose that you have the square root formula expanded to get powers that any power, but to say that one factor
yeah, you can allow n to be a free parameter if that's what you mean. People have experimented with doing that. N equals 3 turns out to be more or less what the data prefer, but it's only very weakly constrained by the data. So as far as integer values are concerned, n equals 2 or n equals 3 both seem fine. Yeah. And I think a non-integer value would be very hard to motivate from a theoretical perspective, since one would have to fine tune an infinite number of terms. So, all right, so this is the summary of where things stood before we looked at the ACT-4 data. Analyzing just CMB from Planck or CB plus large-scale structure, we don't get any evidence for EDE, they're just upper limits. And the basic problem, which I've alluded to, is that increasing H naught obviously means increasing the amount of the EDE, that's the whole idea. But that also then increases S8 and works it to large-scale structure data. So that was why we stated that this model does not restore concordance. And this picture down on the right kind of summarizes the situation as far as H naught was concerned. All right, so why look at this further? The main question that motivated us to do this with ACT is this first one that I've written down. So how robust were these constraints that I showed you to the choice of CMB data set that's used? So what happens if we replace Planck with ACT, or say ACT plus WMAP? As I mentioned, ACT and Planck were consistent at 2.5 sigma in the lambda CDM parameter space, but what about in the EDE parameter space? I want to emphasize that the goal of this paper is not to assess global concordance of this model using the whole variety of cosmological data, but really to focus primarily on the CMB. So use the ACT-4 data. Instead of using WMAP, we actually used a subset of Planck, which is meant to mimic WMAP, and that's for technical reasons, which is just that this Gobaya code doesn't currently have WMAP likelihood. So I found a subset of the Planck TT data, which is basically identical to WMAP. 6 of 1, half dozen of the other. And then for ratings of degeneracies, we use BAO distances and Planck singular. I should mention there was also a second paper from Boulan et al., which came out about a week later, which reached similar conclusions to what I'm going to show you. So let's just jump right to the results. So this is again a triangle plot showing FEDE, the critical redshift, the initial field value, and then H0 and S8. So the red posteriors here are the results for ACT alone. And maybe the main posterior to focus on, at least initially, is this one on the top left. So you can see that the ACT constraints alone do peak at a non-zero value of FEDE. The error bar is large enough from ACT alone that it's sort of consistent at 2 sigma with 0. So that's maybe not the most interesting one to focus on. But after we fold in the low LTT data, which complements ACT in terms of the angular scales that are covered, we get the constraints that are shown in blue. And these now I think are more interesting quantitatively. So the FEDE posterior is still peaked at a non-zero value around 13%. And formally, that posterior is inconsistent with 0 at more than 99.7% confidence. The posteriors are very non-Gaussian, so that's why I tried to put in all like the gory details of the numbers here instead of just counting Gaussian sigmas. But it peaks and is inconsistent. It peaks at a non-zero value, it's inconsistent with 0. For comparison, the constraints on Planck alone are shown in green. That's from the previous work that I just showed you, and that's the one that just gives you an upper limit. So there's some evidence of a tension between these data sets. Yeah.
None of the combinations yet use low L.
It
alone is low L, but the combination that you're doing here, right?
This does not include the full Planck data set. I'll show in just a second. I'll show the results of full Planck. Yeah.
So the blue one doesn't do it.
The green one is the full Planck data set. The blue one includes the lowest TPLs.
It's just a part of the part.
This is a very minor subset of the Planck data. The green one is the full Planck data set. Yeah, which is the results I showed you. Okay, so what happens if we fold in some ancillary data sets? So let's fold in CMB lensing from Planck and BAO to break degeneracies, particularly with omega m. And what's interesting is that although the FEDE posterior does shift down a little bit up here, it's still non-zero. It peaks at about 9%, and it's inconsistent with 0 again at more than 99.7%. The inferred value of H0 in that fit comes in at about 71, which formally would be fine for resolving the discrepancy with low range measurements. So ACT is driving some preference for non-zero amounts of this early dark energy. So important if true, but let's dig into some more of the details here. Okay, so as a comparison, one might ask, what do we get if we do a joint analysis of ACT with the full Planck data set, TT, TE, EE, over the full L range? And that's what's shown in orange here. The other three things are identical to what I just showed you a minute ago. But the orange one now is ACT plus full Planck. And in this case, the full Planck data set carries sufficient statistical weight that you still just get an upper limit, which the FEDE posterior here still peak at 0. Because ACT prefers some non-zero FEDE, the upper limit actually weakens a bit. That goes up to 12%. But Planck carries enough weight that it won't let it go up to a non-zero value with any significance. So H0 in that case comes in at about 69. So this is a curious situation, I think. We spent a long time trying to get to the bottom of what's going on here. So in terms of, to break this down a little bit further, what we're going to do is just look at, where does the preference for this EDE signal come from in ACT? So first, let's compare the quality of the fits in the lambda CDM and EDE cases to these data, and then we're going to look at the residuals. All right, so first, let's look at the chi-squareds. So this is, a frequentist way of assessing the model comparison, but I think it's still quite informative. So this is the chi-squared of the best fit EDE model minus the chi-squared of the best fit lambda CDM model to these data set combinations that I showed you. So for ACT alone, the delta chi-squared is about -9. We have 3 additional parameters, remember, in the EDE scenario. So that corresponds to something like 2 sigma preference. And this, it turns out, is dominated by the improvement in the fit to the EE power spectrum, as I'll show you in just a minute. In the fit with the TT data LS and 650, the delta chi-squared is -15, so it's more significant now. That would correspond to about a 3.2 sigma preference over the CDM. And now the TE data from ACT are also playing a role in addition to EE, as I'll show you in just a second. Okay, after we fold in the BAO and the CMB lensing data, the delta chi-square drops a little bit to minus 12.7. It's the same channels that are driving the improvement. That would correspond to about a 2.8 sigma preference over the CDM. But now once we look at the full Planck data, the story is different. So the fit to Planck alone from my paper last year gave us delta chi-squared of -4. There's 3 additional parameters, so that's not significant at all. And then the fit to ACT plus the full Planck data set gives delta chi-squared of -7. For most of that comes from ACT. So Planck, really isn't showing any preference for this EE, but ACT does seem to drive some preference. So we can look at this in terms of the residuals and the power spectrum to get an even more detailed picture of what's going on. So now I'm showing you the ACT, TT, TE, and EE power spectrum data, and then the middle panels show the residuals with respect to the best fit MSCM and best fit EE models. So wherever you see the light blue circles, being tighter with respect to the 0, that's saying that the EE is providing a better fit. And the one place, if you look at all these plots where there's a significant change, is in the lowest multipole bins in the EE power spectrum. So there's just this handful of bins, 7 multipole bins in EE that are driving the preference within ACT, the early dark energy. And in fact, turns out that it's only the EE power spectrum in one particular sky region that drives this. But it's not seen in both of our sky regions that we looked at. It's only seen in the wide region. So this might give you some reason to worry that there's systematics that are at play. I'll come back to that in a second.
Which function of the sky is this?
So this was our so-called wide region. It covers 2,000 or 3,000 square degrees.
It's a function of the X data.
It's something like 60%.
That's dominant.
It is the larger one in terms of its constraining power. This is true. So if it was a real physical signal, you would expect it to show up in that one first.
If it's a real physical signal, you'd expect what?
You would expect to see the preference coming from that data subset first, because that's more sensitive.
Oh.
Our data subset. Yeah. However, it's also the one which has scans that were taken at lower elevations, which are likely to have more ground pickup in them. So it would also be the one that could have more systematics details. So there's multiple arguments that go both ways for whether you'd expect that to be real or not. So those were the residuals for the fits to ACT alone. Here are the residuals for the fits to ACT plus this low LTT Planck data, which are the yellow data points that are shown up here, are sort of proxy for WMAP. And in this case, in addition to those residuals, LOL and EE still showing up, you also see a coherent difference in TE between the EDE and the CDM fits. So the EDE model can accommodate this basically additive difference in TE, where we just see this coherent negative trend across a wide range of L of 500, L of 2500. And we had known about the fact that our TE looked a bit anomalous in the papers from last year. In fact, there was some, there were some null tests that were borderline failures in the TE data in particular. So it could, again, be a cause for concern as to whether it's systematic. So in the joint fits, the TE and the EE both play a role. So a couple of follow-up plots I've made since the paper came out. So first, if you go back and look at TE, you'll notice that the TE residuals between these two theory curves have this big peak at L of 200. But of course, we actually have data at L of 200 and TE from Planck and from WMAP. So you might actually go look and see if that feature is seen. So that's what this plot is. So this is another residual plot showing the same exact thing, but now with the Planck TE data shown here in green. And if you just look in the bottom panel, I'm showing the residuals. Again, there's that bump that we may have hoped to see, but the Planck data in green don't show evidence for that bump. So I think that it's a combination of the high L Planck TT data, which are very sensitive, not favoring the EDE, and then also this feature in TE not being seen, which are largely responsible for why the Planck data doesn't favor the dark energy like ACT does. Yeah. Yes, this is work in progress. There's a lot of subtle effects that one has to take into account to do that carefully. So there's an entire separate study that's underway to try to do that comparison. Yeah.
So why is it FCL and Planck also measures this much inside?
Yes, you want to compare things both at the map level. You also want to compare them in principle at the power spectrum level. So we're trying to do all of the above. I mean, there's a number of different effects. So the Planck beam varies across the sky. There's temperature polarization leak, it varies across the sky. And if you want to, I mean, we're looking for things at the level of 1 microkelvin squared. So you have to take all the effects into account very carefully. So we're working with people from Planck to do that, the Cambridge group. And I would say that was work that was already in progress before this EDE analysis, but this has provided additional impetus to push that
So
forward.
this is just like a projection of this data on a particular.
That's right.
Lighter-
Absolutely. Yeah, I agree. Absolutely. Okay, so let me just summarize then where things kind of stand from the ACT DR4 EDE fits. So first, a plot just showing the H0 exterior. So the different colors correspond to some of the different data set combinations that I showed you. Solid is the fit to lambda CDM for those data, and then the dashed curves are the fit to early dark energy. So looking at Planck alone is the red curves. You can see Planck alone, there's hardly any shift in H0 as you switch from lambda CDM to EDE. For the other data set combinations that include ACT, then you can get this bigger shift to higher H0 values, which is kind of a striking result, I would say. And for comparison, the background shaded regions show the shoes measurements from Reese and the TRGB measurements from Wendy Friedman's group.
Just so we're. Oh, and that's, I see, okay. And so the orange one doesn't include the.
That's right, yeah. The orange one is ACT DR4 plus the large scale Planck TT plus the lensing plus the beta. So the orange one is probably the most interesting. And I will say it's the BAO data that really plays a significant role in lensing to some extent, but especially the BAO in preventing you from getting up to these really high values of H0. And that's related to the interplay between omega n and H0 in these fits. If we didn't have the BAO, then life would be more interesting. No, I love it. It's great. Okay, and then a summary. You're looking at FEDE. So I showed you this kind of theoretical picture of the type of model we would expect. Earlier. Here's what the actual best fit models looked like. So this is FEDE as a function of redshift, where I've marked the redshift of recombination, and then the redshift of matter radiation equality. So the fit to ACT alone gives you this blue curve, which involves a huge amount of EDE. I think that's maybe not worth focusing on since the error bars are quite large from ACT alone. But then the orange and the green are the direct fits of ACT with the large scale Planck data, and then with CV lensing and BAO. And what's interesting here, there's two features that I find very curious. First of all, the critical redshift is almost right at recombination. So we have this canonical picture in our mind. The dynamics might somehow be tied to the redshift of matter radiation equality. I think that to believe in this, that would just be a spurious hint for model building, I think, because here it looks much more just prior to recombination. The other thing that's curious, which is really what Trey asked about, is that there's no oscillations that you see in these curves. So the initial field value that's preferred in these fits is just slightly perturbed from the minimum of the potential, such that you hardly see any of these oscillations. And in that case, a power law potential may have sufficed all along. So if you take this face value, then you might want to go back to the model building and sort of look at just using a monomial potential, which could be more appealing from a theoretical perspective. So these were considered previously by the Harvard group in the rock and roll paper, but people have found that these axion-like potentials seem to fit the data better. That may have been spurious. Let's see. So I already mentioned this point. The other point I make is that the best fit decay constants are on the order of the Planck mass. Whether that's achievable in string theory, for example, I think is a question. And then the other thing I'll mention is that I never quoted some kind of global consistency metric in the EDE parameter space between these different fits, say to ACT or Planck. And that's because the posteriors are so non-Gaussian that the typical way we quantify this is not really accurate. So I think someone could do an interesting follow-up study applying some of these non-Gaussian tension metrics that have been developed. So I guess I mentioned this point here to see, but at the level of the experiment and the data analysis, these results definitely motivate very careful comparison of actor and Planck, which is work that's underway. And then in terms of the systematics that we're concerned about in this context, so how precise is our transfer function? Again, it's the low L's in EE that are driving things. The lowest L's are where our transfer function becomes non-unity. Ground pickup appears at those L's, polarization as well. I haven't mentioned anything about foregrounds, but it's possible maybe that polarized dust could play some role. I think that our dust modeling is pretty robust and under control, but that's something to perhaps check into. So there's a lot of work ongoing within the ACT team to try to make sure we've got all these things under control.
This comparison would be model independent. So second last, the ACT plane.
Yeah, exactly. So at the level of the data itself. So without making reference to any theoretical model. Okay, so why are we doing all this hard work? So I showed you the ACT-R4 data, which is already quite sensitive. We have collected 4 additional years of data with even more sensitive detector arrays, such that if this EDE model is real, I don't want to guarantee we would detect it in our next analysis, but it's very likely that we would. So there's one final slide here to motivate doing this hard work on the systematics in the future. So all these types of new physics that try to resolve DH0 tension with a change to sound horizon generate signatures in the small scale CMP. So here I'm showing you the differences between the ACT best fit EDE model and the Planck best fit EDE, which looks like Planck times CDM. These plots look basically identical to Planck times CDM. And then similar for the best fits to the ACT plus large scale Planck data combination. And what I want you to focus on is that in TE, you see this large coherent difference across a huge range of L's between these models. And in EE, you also do see some differences. These differences I'm plotting in units of the cosmic variance limited error bar. So this is plus or minus 2 sigma. So you can see we have some coherent difference, which is reaching 2 sigma across a wide range of L's. So if you integrate this up with a rough approximation of our noise levels, which I can't tell you, but when you do that integral, you find out we can distinguish these models at greater than 20 sigma. And this is with data that's on computer hard drives. So if this is something that's real, I think it's very likely we'll know for sure within a year or two. Okay, so I think I'm quite low on time. So let me skip the discussion of primordial magnetic fields. We can talk about this afterwards if people are interested. The takeaway of this part of the talk was that ACT, unlike EDE, ACT does not favor the existence of this primordial magnetic field resolution of the H0 tension. And I'll just wrap up in the last minute or two here with a look ahead. So as I mentioned, we have great data from ACT that we've collected. We're actually still collecting data right now, so it's still active. We think we'll observe at least to the end of this calendar year, maybe partway to next year. Within the context of lemon CDM, if you forecast constraint on H0, we become as good as Planck with data that's already collected. And we think we'll actually surpass the Planck sensitivity. Again, that's just from ACT alone, not even ACT plus WMAP. Of course, our colleagues at the South Pole are also collecting great data with SPT. So again, if this model is real, we should have multiple channels with which to confirm it. Then looking ahead a little bit further, we're building the Simons Observatory right now at the same site where ACT is located in Chile. SO is real, I'll show you the hardware in a second. It's going to start science observations in February 2023. The noise levels are, again, another factor of 3 or so lower than those of ACT, and include 6 frequency channels at arc-minute resolution. So I think many of you are familiar with SO already. This is where it's being cited. There's ACT, class, Simons array, and this is the SO site down here. Here is real hardware that's being built. This is the cryostat that will house the detector arrays for the SO Large Aperture Telescope, containing about 30,000 TES kilometers. And we've applied for funds from NSF to double that number of detectors to completely fill out this focal point. In addition to the Large Aperture Telescope, which will be relevant to all the science I've told you about so far in this talk, we are also building a separate set of instruments, these small aperture telescopes, to look for primordial gravitational waves. So we expect to improve constraints on R by hopefully an order of magnitude within, let's say, 5 to 7 years from now. So I'll wrap up there. Within the context of MCDM, the ACT data confirmed the blank result for H0, ruling out systematics in the CMB as a source of the, let's say, H0 tension as it stood a year or two ago. However, in the context of other cosmological models, we found that ACT and Planck can yield somewhat different parameters where ACT can yield higher H0. Whether this is due to systematics or is real in nature is an open question, which we hope to get an answer to very soon. I do still think that the question of concordance for the EDE model is an open question. It struggles to match large-scale structured data, and I think some additional ingredient or change in that model is needed. Yeah, so let me just mention that it's worth staying excited because all these types of models predict clear deviations in the small-scale power structure in the CMB, and we're going to imminently be able to confirm or refute these hypotheses with ACT and Simon's observatory. So I'll stop there, and thanks for listening.
That's on the subject of trying to make things concordant. If I don't care about having a model that's nice and theoretically motivated and not fine-tuning things, can I draw some arbitrary curve in that FEDE plot that will both move the Hubble tension and S8 in the right direction to match everything, or is that just going to be a generic feature of?
Yeah, that's great. That's a great question. It turns out that a group of people actually looked into exactly this question, and they put a paper out, I think, a week or two ago now. So let me go back to this plot. So yeah, what they did was they basically said, let's parameterize the dark energy density as a function of redshift with a bunch of just free bins with some spline function, basically, from redshift 0 all the way back to redshift 10 to the 5, and then just allow all of those to float. And let's see what the data show. You have to make some assumptions about the properties of the sound speed in addition to the equation of state. But okay, so that's what they did. And interestingly, they find, first of all, some evidence of a peak in the pre-recombination era similar to these axion-like early dark energy scenarios. They also find some, let's say, weaker evidence of another peak at even higher redshifts. I think just, I don't know, somewhere redshift to 50,000, between 50,000 and 100,000. So that's curious if it's real, but they did not find any evidence of anything on standard at lower redshifts, and in particular, they didn't find any amelioration of the S8 tension. So even if you allow, I think they allowed 32 bins to float in redshift, with free amounts of dark energy, and it doesn't appear that any such combination can resolve the S8 tension. And I think that's because, again, late time modifications of such types are super constrained by BAO and supernova data. So you don't have a lot of wiggle room at late times. And then all the early time modifications of this sort generically have the property that they're going to increase omega CH squared, which will worsen the S8 tension. So I don't see a way out through this type of approach. Something slightly different, probably. Yeah, I can send you the reference.
Yeah, great.
Do you know when in the data are sensitive to those ultra high redshifts? 50,000?
Yeah, I asked them that. Their claim was that, so they didn't actually include plots that I remember where they showed residuals as you vary those super high redshift bins, but their claim was that you get small changes in at least the ACT chi-squared as a perturbed dark energy bin. I was surprised because, so one thing I didn't highlight here, but we have played around in these fits with changing the ZC prior range. Let me go back to this plot, for example. So this panel here is the log 10 ZC posterior. And I guess the bottom is cut off, but the range here spans from basic recombination, redshift of 1100, up to redshift of maybe 20 or 30,000. And that's chosen very carefully. If you allow this to be arbitrarily large, then FEDE can take all kinds of crazy values. In particular, if you allow the extremely large values of ZC, you can put tons of stuff out there, and it doesn't change anything in cosmology. As long as it decays away quickly, then it doesn't do anything. So you could then get all kinds of wild things happening in FEDE posterior. So we actually make a choice to restrict only to the range in redshift where such an early dark energy field would have an impact on the H0 tension. So it's like a little bit of fine tuning, even just in the setup of the MCMC itself. Yeah, so again, in doing this exploration, we put it around, I guess a couple of years ago now, with models where ZC is out at like 100,000. And in that case, you don't really see much of a change in CMB. So I'm not exactly sure what their result is being driven by there. Yeah.
On the last slide, you had, you mentioned baryon-clumping, and you also had earlier mentioned magnetic field. Maybe they were correlated. I wondered if you could talk a little about that.
Sure, I'll give you the 1 minute summary. So yeah, this was the paper with David and Arthur, and then with Leander Fields, a student in Princeton, and Arthur's student in Guam. So in this approach, it's a different way of trying to solve the H0 tension. We take advantage of the fact that the recombination rate depends quadratically on the local electron number density, such that if you have a whole bunch of clumping on small scales, then the average of n squared is greater than the average of n squared. So you can speed up recombination so that it happens at an earlier time, and therefore the sound horizon will be smaller. So it's another way of getting a smaller sound horizon. But you also end up generically changing things in the damping tail with whatever type of mechanism you implement to do this. The way that people suggested this before was using primordial magnetic fields, which can dynamically sustain these types of small scale homogeneities. Otherwise, they'd be suppressed by some damping. So what we tried to do was basically just write down a model agnostic version of this baryon-clumping on small scales. This plot just shows that it does move recombination to an earlier redshift. Okay. But the takeaway, let's see, this pretty much shows it. So the takeaway though, if you look both with Planck or with Planck plus ACT data in these models with small scale clumping, you really don't see any shift. So H0 stays down at 68 point something, well below the shoes value, and you don't see any non-zero evidence of this small scale clumping. So in contrast to EDE, I would say that the data don't show evidence of this scenario. There's still a little bit of wiggle room, but to me it doesn't look likely. One way out, one may have hoped, was that the model we're using here is super simple, where the baryon PDF is taken to be time independent, which maybe is not even physical. There's a nice paper from Danum and Yassine a few months later, just recently, that they allowed time dependence in that small scale baryon PDF, but they don't find that helps to illustrate the situation. Correct me if that's not the case, but that's my takeaway.
When you have the different combinations of data, when you do these different tests, and some of them you completed, you were saying last year.
Yeah.
So the Boltzmann accuracy is same.
Oh, that's a good question. So yeah, I should note that the default settings in all the Boltzmann codes were actually tuned to work for Planck. So that's why no one's thought about it in like 10 years. Planck's been the state of the art for 10 years. You can find there's that paper by Julian on this board where he actually details how he determined the fiducial settings, and it was by comparing to forecasts for Planck. So that was why nobody thought about this in a long time. The reason that it matters for ACT is that we're measuring things on smaller scales than Planck. So Planck cuts off by 2000, 2500 maybe. The ACT likelihood goes up to almost 4100. And so that you do have a little bit of sensitivity to those high L's where I showed that this accuracy setting has an impact. So that's why it hadn't been noticed previously. Yeah, it would have been bad if we had noticed it before SO and S4. But, yeah.
If you're going to that high, have you tried different program treatments to see results change?
That's also a very good question. Yeah, So we did not, I mean, so in the ACT analysis, right, we have a full detailed foreground model for all the secondary anisotropies. We didn't change anything involving that for these purposes. In fact, we're using this likelihood where you marginalize out all those foregrounds in advance, and you parameterize the CMB with another band powers, which can then be fit to any theoretical model that you want with the CMB. So the part of the machinery we're changing is just the part that predicts the CMB power spectrum. And all the foreground stuff is left as it was. Yeah, I mean, I agree for things like SO and S4, we should also revisit the accuracy of those high foreground models and make sure that everything is totally kosher out there. Was there any questions on Zoom?
I don't see any questions. I would just like to say that Colin is here today. He's staying afterwards if you want to chat. He's in the visitors room, room number 950. So feel free to reach out. There are no more questions. Let's thank Colin.